Today we are doing a two-sample proportion significance test. So yesterday I think we did a confidence interval, so here we are in the test. The problem that we're going to be working on today is our teenagers going deaf. So in a study of 3,000 randomly selected teenagers, this is in 1988 to 1994, 15% showed hearing loss. And then in a similar study, 2005-2006, 19.5% showed some hearing loss. So I've pulled these variables out. In letter A, this is how I know I'm doing a significance test. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? So that's what we're looking for. We need evidence. When it asks you for that, you're going to do a significance test. So I've already written down. Let me move this over and zoom out. Let's make sure I'm good. Here we are. Okay. So P1. This was 1984. And then here is in the 2000 P2. So I just pulled those sample proportions. Now we're going back to a significance test. And remember, on a significance test, we're going to be doing, we have to have our HO and our HA. Okay. Now, for this, this is a proportion. Hopefully that's obvious at this point. What we're going to be testing is, and what I'm going to end up doing is, I'm actually going to take, I like positive numbers. So I'm going to take pi 2 minus pi 1 and the assumption is that there is no difference. So that's going to be equal to 0. So there's no difference in the sample proportion. And then here, notice how it stays exactly the same. So pi 2 minus pi 1. But what we want to show is that it is actually greater than 0. Okay, so greater than 0. Because what we're trying to show is that there's an increased hearing loss in 2000. So right here, this is the 2000s, and then this is the 1900s, where I spent a good majority of my life. Okay, so here we are. The one thing that has to be defined are the parameters. So it's extremely important that we define this. So pi 2 is the population proportion of hearing loss for teens in 2005 to 2006. Pi 1 is the population proportion of hearing loss, I need to add in loss, for teens 1988 to 1994. Okay? So all that really has to be defined here is your, we have to write our HO and HA because we're doing a significance test, and then pi 2 and pi 1 has to be defined. So I don't have to go here. These are coming from samples, and that's, you don't have to define that. Now, leave a little space in the variables, because lucky for us, there's something new appearing in the significance test. So I'm going to leave just a little space, and let's title this. This is conditions for a two-sample proportion Sig test. And we don't have to worry about degrees of freedom because that's only for means. Number 1. Now yesterday was actually an experiment, I believe. And so that was like kind of maybe the first time, maybe I have done it before with you, where, it wasn't a simple random sample. It was randomized experiment that was done. Well, this is not an experiment. This was actually a sample, from 3,000 people and 1,800 people. So we go back to simple random sample, but we have to add this new word because it's two samples. You'll lose a point if you don't have this. We need them to be independent, simple random samples from the population of 2005, 2006 teens and 1988 to 1994 teens. This is important. We need those two samples to be independent of each other. And there's no reason to believe these were two separate samples. Are independent, okay? So knowing what happened with the first sample shouldn't affect what happens with the second. Now number two, we are sampling again, so population greater than 10n, we're not replacing, is going to come into play. But now you have two populations to worry about. So we actually have to check the population teens 2005 to 2006 greater than 10n, and the population of teens 1988 to 1994 is greater than 10n. So yay, we have to do everything twice. Equals 10 times. Now, remember, my 2000s is actually down right here. That's P2, because I did larger minus smaller. So that's 10 times 1,800. And then this is 10 times 3,000. Okay, so more than 18,000 teens in the year 2005, 2006, yes. So we would say yes. So the first two conditions tell us that we have independent teens. Now I get to the third condition. And the third condition is for proportions. We've got n times pi and n times 1 minus pi. It might be n times p hat, n times 1 minus p hat if you were doing a confidence interval and don't know it. So what ends up happening here, guys, is we don't have each individual pi. We don't know that. So the next best thing that we can use for each of these distributions is using the p hats. If you don't have pi, you can't use it. If you do, you use the Greek letter. So number 3, I'm going to check both of them. And it's as obnoxious. I know it is. You're doing it twice. And I guess we could do 1 p hat 1 and 1 minus p hat 1 and 2 p hat 2 and 2 1 minus p hat 2. All of these have to be greater than or equal to 10. So equals. What do we got? 3,000 times 0.15. It's coming from up there. 3,000 times 1 minus 0.15. What do we got here? 1,800 times 0.195. And 1,800 times 1 minus 0.195. Doing everything twice. So we've got, let's see, I'll just do it in my calculator really quick. Hopefully you are doing it. So I got 450. I've got, I think, 2,550. And then I have 351 and 1,449. Okay, and all of these are greater than or equal to 10. So what that allows us to do is use a normal approximation is okay. Okay, so I draw my normal curve. This is probably the worst. This is as bad as any stats problem is going to get, is right here. This is probably the worst it's going to get. It only gets better from here. Less writing. So, I'm trying to decide what goes in the curve. If you have the Greek letter, you're going to use that. Remember, this sampling distribution is actually bringing two distributions together. It's bringing the 1900s one and the 2000, and it's putting it as a difference on this one curve right here. So in the middle of this curve, always look to your HO and HA if you're doing a significance test. 0 is going on that curve. Now, this is all about the differences. Pi 2 minus pi 1. So it's a bunch of p hats of differences. So the other thing that we need to put on this curve is the difference of our sample proportions. I'm going to go up here, and let's have done that right here. So if I were to take, I'm going to add kind of another variable, and that's because you need to model what your HO and HA are doing. If you subtract the pi's to get a difference, we need to subtract our p hats. So I do p2 minus p hat 1 because I like larger numbers minus smaller numbers give me positive. So 0.195 minus 0.15, 0.195 minus 0.15 is equal to 0.045. So I come down here, and that's what's going to go on the curve is 0.045. And I'm shading greater than, because that's what my alternative is. Okay, so now I go to the formula. Okay, page 5 of my grape sheet. You have a lime sheet. You are doing a significance test. So you are going to take your statistic minus the parameter divided by the standard deviation of the statistic. Okay, so I'm using that. Your statistic is differences of your p hats. Your parameter is the differences of your pi's. The standard deviation of the statistic is going to be down where you used it yesterday. I'm on a 2-sample problem with proportions, and this is the formula that you're going to use. See it? Okay. So here I am. Statistic p hat 2 minus p hat 1 minus parameter pi 2 minus pi 1 divided by the standard deviation of the statistic. Now, let's stop here for a second. Don't get ahead of Now, yesterday we didn't have each individual pi's, so we used p hat, p hat, p hat, p hat. Today is going to be a little weird, and today, and it only happens on this type of problem, 2-sample proportion significance test, we are going to do this thing called pull your p's. And what that entails, I need a little more room up here, is this, okay? We assume that there is no difference between these two proportions. We do not make that assumption when you are doing a confidence interval, but we do make it here that these two things are, coming from the same proportion. So why not just put everything together? So let's just look at here. So 15%, that came from, if I take 0.15 times 3,000, that came from 450 teens who were showing hearing loss divided by 3,000. And this 0.195 came from 0.195 times 1800 is 351 divided by 1800. So what ends up happening is, because of our assumption that there is no difference in the parameters, we're just going to put these together. And so we have to pool our P's. We only do it on a two-sample proportion Sig test. It's the only time you do it. And what that means is, let's just put the two samples together. So I have 3,000, 1,900 people. I've got 1,800 in the 2,000 teens. And out of those, how many of total were hearing loss? We would take 450 plus 351. Do you guys see how we pull? We're bringing the two samples together to just represent one sample of total hearing loss, because the assumption is that there is no difference. So let's just go with that. So we have 4,800 total teens, and 450 plus 351 makes for 801, which when you divide that is going to give you a p-hat pooled of 0.167. Okay, and the only place that this 0.167 is going to show up is when you go to do your standard deviation formula. So I come down here, 0.167, and I'm doing the standard deviation. This is coming from my live sheet. It's an ugly looking formula. But instead of doing p hat 1 times 1 minus p hat 1 and p hat 2 times 1 minus p hat 2, you're going to actually do p hat pooled 1 minus p hat pooled over n1 plus p hat pooled 1 minus p hat pooled n2. You only do this on a significance test for proportions. So p hat pooled 1 minus p hat pooled over n1 plus p hat pooled 1 minus p hat pooled over n2. Formula, substitution. So we've got 0.045 minus 0 over the square root. 0.167 times 0.1 minus 0.167 over 3,000. Plus 0.167, 1 minus 0.167 over 1,800. It's very ugly. Like I said, it's the worst it's going to get. So now I go here, the calculator, stat test, two sample. And it's not a proportion, so I'm sorry, it is a proportion, so you better choose 5 or 6. And it's 6 because it's two sample. Now what's really interesting about this, guys, and this goes back to when you did when you were back in confidence intervals. The calculator doesn't want the 15%. The calculator wants to know the fraction that gave you 15%. So if you took 0.15, 15% of 3,000, that's going to give you the 450 out of 3,000. And P2 was creating by taking 351 out of 1,800. And I can find that out by taking 19.5% times 1,800 gives me the 351. But I totally just entered that wrong, because the calculator, if I wanted to subtract this minus this, so that I have a larger p hat difference, 0.195 minus 0.15, I actually have to enter my p hat 2 first. So I got to change that. So this should be 351 out of 1,800, and then 450 out of 3,000. So I have to do that because I want it to take the larger proportion minus the smaller proportion. And that's how the calculator doesn't know the difference. It's always going to subtract the p hat 1 minus p hat 2, whatever you enter it. So I'm going to do a greater than, so just go to the go up, greater than, hit calculate. Okay, so Z, 4.04. P-value, very, very small. And then it kind of spits out your p hat 1 and p hat 2 just to check it. Oh, and there's a new p showing up. There's your 0.167. So the calculator never asks you if you want to pull your p's. It actually does it automatically. So you might do this test and forget to pull your p's, and you'll get to this test and be like, oh no, there's a p hat, another p hat showing up, and you can go back and fix that. So it won't show up in a confidence interval. It only shows up in a significance test. So I'm going to copy those numbers down. Z is 4.05. Whoa, I didn't even write. Bad me. You should be doing Z equals. Please don't forget that. The p-value is 2.58 times 10 to the negative 5th. This is a Plar situation. So I will end this with my conclusion. So since the p-value is less than alpha equals 0.05, we reject HO. And now I just kind of look at the sentence they started with. There is sufficient evidence to conclude. And what are we trying to conclude? It says that the proportion of teens with hearing loss has increased. Proportion of teens with hearing loss has increased. So let's just zoom out and look at the beauty of this problem. Look how smart we look. This is as bad as it's going to get. You have that new p hat pulled showing up. Let me just point out that the p hat pulled is all you're doing to calculate it is you're bringing the two samples together. You don't do this in a significance or a confidence interval. You only pull your p's for a significance test. The reason is because you said that there was no difference, so let's just put these samples together and just create one huge sample of 4,800 people and 801 teens that had their hearing loss. So that sums up a two-sample proportion significance test. Hope you guys have a good day.